Hello, my name is Vincent Ramon, and my team will be going over modeling space radiation cancer risks. So, we're going to ask ourselves, how do we mitigate radiation-induced cancers for our astronauts? So, our team questioned, can we optimize radiation shielding and individualized mission planning to significantly reduce astronauts' lifetime risk of radiation-induced cancers during missions? We created a model to reduce radiation-induced cancers and optimize astronauts' health during their time in space. And here in slide 3, we have kind of a model of the space radiation cancer risks, going over our risk model, setting up simulation and data, and then applying that and the impact that it has on our astronauts. So our hypothesis will go over if gadolinium/boron doped hybrid composite material was used to create a radiation shield in astronaut containing spacecraft. Overall levels of radiation exposure and thus cancer risk would be reduced due to the gadolinium and boron having the highest thermal neutron capture cross sections of any materials. We will create a mathematical model combining radiation dose, shielding effectiveness, and astronaut-specific biological factors to predict cancer risk and identifying strategies that reduce lifetime cancer probability without the excessive spacecraft mass.
As humans prepare for longer missions beyond Earth's protective magnetic field, radiation-induced cancer has become one of NASA's most significant human health concerns. Unlike radiation on Earth, astronauts in deep space are exposed to high-energy particles that can damage DNA and increase their lifetime risk of developing cancer. NASA's Human Research Program is currently investigating strategies such as improved shielding materials, pharmaceutical countermeasures, and faster spacecraft to reduce radiation exposure time. This project develops a mathematical model to calculate risk of radiation-induced cancer.
What is radiation? So, radiation is energy that moves from one place to another in the form of waves or particles. And it comes in two different forms. The first form is going to be non-ionizing radiation. That's going to be the lower energy radiation that's not energetic enough to detach to electrons from atoms or molecules. The examples of this would be radio and cell phones, microwaves, infrared waves, things of that nature. The second form would be ionizing radiation, which is a type of radiation of such energy that it can detach electrons from atoms or molecules, which causes change at the atomic level when interacting with matter, including living organisms. Examples of ionizing radiation would be closer to ultraviolet rays, different X-rays, things of like CT scans, as well as gamma rays. So why is radiation so dangerous? So radiation causes molecular destruction, or it can cause molecular destruction. It can cause DNA damage, which causes direct double-strand breaks and indirect damage by ionizing water to create free radicals. It also causes failure to repair, which it has high linear energy transfer, particles that cause clustered lesions that are significantly harder for cells to repair than terrestrial radiation. So the systemic health risks. What does this bring to our astronauts, basically? What health risks does this cause? So in an acute form and in high doses, there is something that's called ARS, or acute radiation syndrome. This could be characterized by GI distress, hemorrhaging, or neurovascular symptoms like seizures. Another chronic or long-term effect would be carcinogenesis, or higher risk of leukemia and solid tumors. That would be either in the lungs, stomach, or colon. There's also degenerative which would be the development of cataracts, cardiovascular disease, and CNS cognitive impairment. Kind of similar to dementia in a way. So in context with everything, especially with our astronauts that would go into deep space, exposure levels beyond Earth's magnetosphere, radiation is 100, even to 1,000 times higher than on Earth. There's also a 1 to 365 rule that says that 1 day of deep space exposure is equivalent to 1 full year of radiation on Earth, as well as mission doses. A Mars mission could even exceed 1,200 MSVs, which, is well beyond the standard 3% lifetime cancer risk limit.
For this project, it is important to understand what a millisievert is. A millisievert, or MSV, is a unit used to measure the effect of ionizing radiation on the human body, accounting for both the type of radiation and the sensitivity of each tissues. Using millisievert allows researchers to assess risk of long-term effects like cancer from radiation, compare radiation exposure from different environments. It also provides a standardized way to measure radiation. This chart on the right provides a breakdown of different MSV exposure to help demonstrate the amount of radiation exposure it takes to cause harm. A dental X-ray is going to be 0.01 MSV, while high doses around 100 MSV will cause potential illness. Understanding MSV measurements allows for monitoring, managing, and minimizing radiation exposure effectively. To address the risk of radiation-induced cancers, we developed an individual cancer risk calculator based on a mathematical model. The purpose of this calculator is to estimate how different mission conditions influence an astronaut's radiation exposure and potential lifetime cancer risk. The model takes several mission-specific factors into account, including the duration of the mission, the radiation environment, the thickness and material of spacecraft shielding, and any previous radiation exposure. These inputs allow the model to first estimate the total radiation dose received during the mission. That dose is then used to estimate the associated lifetime risk of developing radiation-induced cancer. Dose received is a linear function of the exposure time. R times T equals radiation dose, where R is the radiation dose rate and T is the mission duration measured in days. Looking at this graph, it demonstrates that Mars is going to have a greater radiation dose rate compared to the International Space Station due to it being farther away from Earth's magnetic field. When accounting for shielding, we use exponential attenuation equation. This formula models the effectiveness of different shielding materials by allowing researchers to compare the attenuation coefficients. By evaluating different materials, researchers can identify effective shielding strategies that help protect astronauts from radiation-induced health implications. By adding previous radiation exposure dose rate to the shielded radiation dose rate, we can further evaluate the cancer risk. To finish the equation, you multiply K times D total, where K is the lifetime cancer risk coefficient. The model estimates lifetime excess cancer risk by multiplying the total effective radiation dose by a literature-derived nominal risk coefficient. This coefficient represents the average increase in lifetime cancer risk per sievert as radiation exposure and serves as a simplified approximation for comparing mitigation strategies. According to ICRP, a commonly used nominal value for the lifetime cancer risk coefficient is K equals 0.05, corresponding to an estimated 5% increase in lifetime cancer risk per sievert of radiation. Engineering questions the model can evaluate. How does increasing shielding thickness affect astronauts' radiation exposure? Which shielding material provides the greatest reduction in radiation dose? How does mission duration influence overall radiation dose astronauts are exposed to? Which combination of shielding materials and thickness minimizes predicted lifetime cancer risk?
So now we're going to look at some current and previous solutions that engineers have used to solve this radiation problem. So in 1958, with the launch of Explorer 1, Van Allen radiation belts were discovered, as you can see in that diagram there. It's kind of showing how they're surrounding the Earth's magnetic field. They consist of high energy particles originating predominantly from solar winds, and they become captured by Earth's magnetic field. And this discovery led to the need for radiation protection for the following manned ventures. So after the discovery, in the 1960s, engineers simply used the protection of the aluminum honeycomb shell that outer walls of the spacecraft were built out of. This was put into place in order to block high energy particles. And this even went into the 70s, more towards the mid 70s as well with this design. Also, heavy objects like water tanks and food supplies were placed along the inner walls to further attempt to protect individuals inside. The limits of this were harmful secondary radiation that would emit from the metal sections of the wall, which is of course not good for our astronauts. And this was realized in the 90s and 2000s that aluminum, just plainly aluminum walls could be dangerous for our astronauts due to secondary radiation. And engineers solved this by adding polyethylene blocks to the sleeping quarters of the spacecraft. And this was due to the hydrogen-dense content of polyethylene, which stopped particles without creating harmful secondary rays. It was slightly less effective in blocking high energy particles, but it did prevent that secondary radiation, which was the biggest concern at the time, which greatly reduced the risk of cancer. Now, more towards 2016 to the modern day, high density polyethylene, which is a hydrogen rich material, is used to effectively capture and slow down cosmic radiation. This is currently used in combination with polymers and structural composites to craft spacecraft hulls. This material is great due to its effectiveness at capturing low energy radiation, as well as preventing high energy rays from producing secondary radiation. And it has all of these properties while being lightweight and comparatively easy to bring on board. Every single material and pound that you bring up to a spacecraft is going to cost an immense amount of money. So anything that we can do to reduce this weight while still keeping the desired effect is a great plus. Now, the only limitations are that the material is not perfect to counter high energy radiation. This is our proposal here. Gadolinium boron doped composite material. And this would be kind of like a 3-layer system of protection instead of just one wall that protects against radiation. This uses both the benefits of elements gadolinium and boron with the lightweight benefits of carbon fiber as well. Higher weight variants, which would include more gadolinium, could be especially useful for sleeping quarters, and they would have the best chance at reducing risk of cancer. So here are the results for each kind of historical solution of our radiation problem. And using the mathematical model for the aluminum shell design of the 60s and later into the 70s as well. So using our model and the standard thickness of 4.5 centimeters, we're going to be assuming 2 millisievert average daily deep space dosage, which is essentially just how much the astronauts receive per day over a 365-day mission. So plugging it into our model, an astronaut would receive about 559.78 millisieverts of radiation using an aluminum shield, and this provides us with a cancer risk of 27.99%. Going into polyethylene and using our model, we get a significantly higher value of 681.82 millisieverts of radiation. And you would think, with the advancement of technology, why is it higher? And this is because polyethylene and other lighter materials are not great at protecting from extreme high energy radiation. These calculations used higher energy particles to test them. And of course, these lighter materials are not great at countering those, whereas aluminum is a little bit heavier in weight and is better at countering high energy radiation. which is why when you put it at a lower and more common level, an astronaut would only receive 360.81 millisieverts of radiation in a one-year trip. Now this brings down the cancer risk to 18.04%. Now these high-density polyethylene blocks with an updated linear attenuation coefficient are going to give us a dosage of around 352.59 millisieverts of radiation. This brings down the cancer risk to 17.63. And the amazing thing about this material is that it slightly improves on the normal polyethylene lower energy blockage, but it also excels in the presence of higher energy radiation, which kind of fixes the problem of this previous issue here where it was a lot higher with higher radiation levels. And this is why this material has continued to be used today, because it kind of gives good protection for both types of environments. Now for our custom composite material here, which is 15% weight gadolinium, 5% weight boron, 80% weight high-density polyethylene, using the same thickness, we only get 86.797 millisieverts of radiation. This brings down the cancer risk to only 4.34. And obviously these are theoretical values because this material does not exist in spacecraft yet, but this result is lower than the lowest dosage that is documented to have resulted in cancer, which would be 100 millisieverts. Now, higher energy radiation causes similar behavior to high-density polyethylene, which means a storm room with a higher percentage of gadolinium and boron could be created to get the best of both worlds scenario, meaning that you could have you can kind of customize these percentages here to get the best benefit for the different types of environment. Let's say if there's a solar storm or a solar flare that increases the energy of the radiation, then you can go into the storm room, which would have, let's say, more percentage of gadolinium. But this composite here is just for your standard average environment, which obviously is changing a lot, but this is more just for an average estimate. So the culmination of our results are here in this table, and as you can see, over time we obviously got better at preventing the cancer risk in our yearly exposure of radiation. And using the mathematical model that we created, we were able to get some pretty good results for our material. And the table doesn't tell the full story because it is slightly less effective than high-density polyethylene when it comes to higher energy radiation. But of course, as I said earlier, with implementation of storm rooms, this factor can kind of be rectified. So current knowledge is familiar with gadolinium and boron dope material, but gadolinium has never been used in a spacecraft. The gadolinium boron dope composite material is a combination of the useful traits of 3 different materials, leading to our version of the best protection for astronauts in space against radiation. Now, gadolinium, along with nanoscale technology, is currently being researched, and what I was reading about is that it could provide better protection and more versatile materials to kind of rectify the issues with high energy radiation. Now, multi-level radiation testing would need to occur for our theoretical values to be verified, and of course spacecraft would have to implement a section of composite material to see its actual effectiveness in space. Overall, we were able to deepen our understanding of radiation, space history, cancer risk, and higher mathematics with this project.
So limitations. Every project has limitations, and ours is no different. All engineers eventually have to deal with limitations that hinder projects and have unknown variables that can totally throw everything off course. So here are a few we have considered. One limitation would be simplified radiation environment. So our model assumes a constant radiation dose rate, but radiation exposures vary throughout different missions due to solar particle events such as solar flares, and even in changes in spacecraft positioning. A second limitation would be shielding assumptions. So we are assuming a uniform shielding around the spacecraft, whereas real spacecraft have varying thicknesses and materials throughout the whole structure. A third limitation would be a linear cancer risk estimate. So the relationship between radiation dose and cancer risk is way more complex than our simplified mathematical model and may not capture all biological responses. So these are improvements that can be implemented in future projects. They consist of AI mission planning. A second improvement would be active magnetic shielding. So having that magnetic shielding protect our astronauts from that radiation. A third improvement would be real-time radiation sensors. So these radiation sensors would detect, obviously extreme large amounts of radiation, which could potentially, save our astronauts who are up in space. And a fourth future improvement would be handpicking astronauts with personalized genetics. So basically, handpicking our astronauts who would have a better life expectancy in those long-term space missions. In conclusion, our takeaways is that radiation remains NASA's greatest human health risk, as well as our mathematical models predicts how shielding and mission duration affect lifetime cancer risk. And optimizing shielding and mission planning could significantly improve astronaut safety during missions to the moon, Mars, and hopefully even farther than our solar system. And here is our multiple references that we use for our project. Thank you.